remembering how things work in flat space and how to do conformal convectifications. And then we moved on to defining a notion of what it means to be asymptotically flat. That is, where the metric, far away from anything interesting that's happening, looks like Minkowski space, but then there are 1/r corrections that encode the interesting aspects of whatever interesting stuff is going on inside the spacetime. So that's the first part. Now, in today's lecture, we're going to start discussing the symmetries of asymptotically flat spacetimes. Yesterday, I grouped these two items here under one and called it symmetries and observables, but I feel like this deserves its own bullet point. So we're going to discuss these two in the first lecture this morning, so symmetries and associated observables, which go under the name of memory. And then in the second lecture this morning, because we have two, we have full blast 4 hours, marathon. In the second part, we're going to focus on aspects of scattering, and in particular, when we take the low energy limit. And then we're going to relate these three items in what is referred to as the infrared triangle. And then towards the end of the second lecture today, we're going to start getting a flavor of how things could be holographic in asymptotically flat space. And then continue tomorrow with mentioning some of these aspects in more detail. But before I continue, let me ask, are there any questions on yesterday's lecture that are important for moving on now and cannot wait until the Q&A today? Yes? The what? Yeah, we're going to talk quite a lot about what's happening on the celestial sphere in this fifth bullet point up there. So that will be a focus in the second lecture today and then the lecture tomorrow. Okay, so if there are no more questions on yesterday's lecture, let me jump right into it. So one thing that we discussed at the end of the lecture yesterday was isometries of Minkowski space, which are defined by a vector field psi that is an isometry if the Lie derivative with respect to it, when acting on our metric, which we started with flat space, so that's just the Minkowski flat space metric, when this is equal to 0, or equivalently when the covariant derivative on this vector field symmetrized vanishes. Today we're going to discuss a more, let's say, relaxed notion of symmetry, which goes under the name of asymptotic symmetry. And there we don't enforce this equation exactly, but we want to look at symmetries in the asymptotic region of the spacetime. So let's now put our general asymptotic flat metric G mu nu, and let's impose that this vanishes as our radial coordinate goes to infinity. So that's the definition. The Killing equation must be satisfied asymptotically. And if you can find such a vector field, psi, that does that, then this vector field will go under the name of large diffeomorphism. Which means that it preserves the asymptotic form of the metric but it leads to non-trivial charges. And that means that we are looking, if we're acting with this diffeomorphism vector field psi, then we are looking at physically distinct spacetimes. And these charges will give us a label that distinguishes between these physically distinct spacetimes. And these large diffeomorphisms, the fact that they give rise to non-trivial charges, is in contrast to what is sometimes called small diffeos, which are nothing but a redundancy of the theory. Okay. So let me maybe depict this as follows. If you have a diffeomorphism that has only compact support in your space-time, then this would be what vanishes as you go to the boundary. Then this would be a small diffeomorphism, shows the coordinate transformation and the redundancy of the theory. But if this transformation has non-trivial support on the boundary in the asymptotic region, then this will be referred to as a large diffeomorphism. Now you know about small diffeomorphisms, both in GR and in quantum field theory. We refer to them as gauge symmetry, which is really just a redundancy. And these large diffeomorphisms, there's also large gauge transformations in like Maxwell theory, for example. These large diffeomorphisms do something non-trivial. Okay, so this is an important distinction. So the question that I want to ask now is, what are the asymptotic symmetries, I will abbreviate them like that, of our favorite theory of gravity, which I hope you agree with me is Einstein gravity, in asymptotically flat spacetimes. So what that means is that we go to r equals infinity. We talked about how the metric becomes flat at leading order, and then they're one of our corrections. So that means that in this asymptotic region, gravity becomes weak. It's flat up to these corrections. And so you can make a guess what the asymptotic symmetry group should be. Since gravity is weak, curvature is low, what would you guess is the asymptotic symmetry group? Those of you who already know, please refrain from answering. Yeah, you would expect it to be the Poincaré group, right? Like GR becomes special relativity far away, so it should be the Poincaré group. But that's wrong. So it turns out that the asymptotic symmetry group of Einstein gravity in asymptotic flat space is an extension of the Poincaré group, and perhaps the worst possible extension because it's an infinite dimensional extension. So in order to see that this is the case, what we have to do is we have to find all these diffeomorphism vector fields that are large diffeomorphisms of asymptotic flat spacetimes. So your task is now to find all the vector fields psi such that the Lie derivative vanishes asymptotically. And here we're gonna put in the asymptotic fall-offs that we discussed yesterday. So the ones that we refer to as coming from Bondi, Vandenberg, Metzen, and Sachs. And then we compute. We try to find all these vector fields psi. Asymptotically flat space. Sorry. Asymptotic symmetries and asymptotically flat. Okay, so We're going to make an ansatz here because it's a bit complicated to, full blast try to find all the vector fields xi. So what we're going to do is, so we already know that Poincare has to be part of that symmetry group, but we're going to drop the Lorentz group. We just, look for vector fields that do not cover rotations and boosts to make our life simple. So we assume some form for these vector fields xi with xi u being of order 1, xi r being of order 1, and xi a being of order 1 over r. So these fall-offs of this ansatz for the vector field will eliminate rotations and boosts. They should still contain, they still contain translations. And now we're going to take it from there. So let me remind you that the Lie derivative of some metric is given by this form. And this we want to be vanishing asymptotically. And now in order to find these vector fields, we're going to remember that we defined this metric in a particular gauge, the Bondi-Sachs gauge, or Bondi gauge, which meant that GRR downstairs and GRA downstairs are 0. And this is exactly 0. And this we want to keep exactly 0 as we act with this Lie derivative. So that's the first thing. And then the second thing is we want to preserve the BMS fall-offs. So these were the fall-offs for the other metric components, GUU, GUA, and so on, that we wrote down yesterday, which had a particular 1 over r corrections after the flat metric. All right. So let's do this in a little bit, in some detail, so that you actually, get a grasp of what's going on here. So let's start with one of these gauge conditions. Let's start with GRR being exactly 0. So what that means is that if we act with the Lie derivative on the metric component GRR, we should still get 0. So 0 should be exactly, this should be exactly satisfied. So let me write this out. So there's some xi rho, nabla rho, GRR plus 2 nabla r xi rho, g rho r. That's just writing out this equation. Now we know that the GRR that we started with is exactly 0. And we also know that when the component rho here is A, then this is also exactly 0. So the only thing that rho can be is u. So that means this rho is u. So that means that I have minus 2 nabla r xi u, because the GUR component was minus 1. And now I have to work out the Christoffel symbols of the asymptotically flat metric in these Bondi coordinates in order to write this as a partial. So there is one Christoffel symbol that fits in here that is non-vanishing. Well, there's some here. If you plug this in when you write out the covariant derivative, then what this means is, so this thing has to be 0. There will be a r derivative that acts on xi u. So from imposing that the Bondi gauge condition holds when acted upon with this unknown diffeomorphism vector field xi, we'll learn that the partial dr on xi u is 0, So psi u is just a function of u and the angles, but not r. So put this in, that all the Christoffels that are relevant here vanish, and then this is what you get. From GUR being -1 at leading order. Okay? Okay, so that was one of the conditions. Let's look at the other one. So the other one is GRA exactly 0. So that means that, again, the Lie derivative with respect of the vector field now acting on GRA has to be 0. Let me do this one also in some detail. So again, I'm just writing out the formula. Okay, so same story here. This has to be a U. Then that is a U. This row can in principle be U or some angle coordinate. Let me call it B. And then that one as well. So that this term gives something non-vanishing. But we just learned that the psi U component is independent of R. And so hit by this, it will be 0. So the only really thing that is left here is the angular component. So now I'm writing out this expression, remembering that the leading term in GAB is R square gamma AB. So there's R square gamma AB here. Double R psi B. Oh, I forgot to say this was, of course, also 0 by the gauge condition. And then this one, similar as before, GRU is -1, so I get the minus nabla A psi U. So now I want to express the covariant derivatives by partials. The relevant Christoffel symbol in this computation is gamma BRA, which is 1 over R times Kronecker delta at leading order. And so plugging that into here, I get the following expression. So this D here will denote the covariant derivative on the sphere, while the nabla was the covariant derivative of the whole metric. And we're gonna raise and lower indices on the sphere with the sphere metric. So dA downstairs would be gamma AB, dB upstairs. Okay? So now so we see that this has to be vanishing. And what this then tells us is that the R derivative of psi B, the angular component, is 1 over R square dB psi U. And from there we learn up to an integration constant that psi B, or let me call it psi A, is -1 over R dA psi U. Okay? So by just invoking the gauge condition that this is satisfied exactly, we have found out that the U component of this putative diffeomorphism vector field is independent of R, and that the angular component is given by that U component. Okay? Any questions so far? Yes? Yesterday, okay, there's several ways to discuss asymptotic flatness and to discuss symmetries of such spacetimes. I have, for illustrational purposes, chosen a coordinate-dependent way of doing that. There's also coordinate-independent ways, which I will make some comments about in a little while. In this form, I chose my metric in such a way that it naturally was geared towards discussing light cones and radiation. And this is a good coordinate system to discuss the physics near non-infinity. We also discussed that it's not a good coordinate system to discuss like the future or the past time-like boundary and so on, so there we choose other coordinates. But for the purpose of discussing radiation and how, for example, symmetries act at the null boundary, this is a good coordinate system. And so this is how we got these two gauge conditions on the RR and RA component, and then we had these fall-offs. You could choose a different coordinate system, and then the details would look different. But unless there's some weird coordinate system that completely obscures some aspect of physics, the answers that you should get are the same. Yeah. Okay, so we're doing this explicit computation just so that you see that it's not so hard to understand what the asymptotic symmetry group of asymptotic flat space is. You can do it. So we have already done half of it. We have used the gauge conditions. We have found out that this is the condition on psi u, this is the condition on psi a, and now we have to use the fall-offs in order to completely nail down what these should be. I'm gonna do one more, and then the other one is a homework exercise for you. And if you have trouble, you can ask me in one of the Q&A sessions. So we're gonna do one more. And the one that we're gonna do is the GUR component, which if you look into your notes from yesterday, had to be such that they fall off as 1 over r squared. So we impose that the linear derivative on the UR component goes as such. Let me again do this. So this is now going to be a two-liner. Let me write this out again. So this is of order r to the minus 2. So if I look at satisfying this equation at one order above, then this will be subleading. So let's look if the other ones are more leading. So indeed, we have something more leading here because when this rho is u, then we have something of order 1. So actually, so let me recall. This is minus 1 plus 1 over r squared, but the derivative kills the 1, so then it's more subleading in r. Okay, this one, we have fixed the rho component to be u, and this one could have the rho being a or r. So now let me drop this term, because I already see that I have more leading terms than 1 over r squared or 1 over r cubed. So this would be subleading. So the more leading order, the things that I have to keep are this, so minus 1 from GUR, W psi u, and then minus, because there's the u r component will have a minus 1, so minus nabla r psi r, and then another term, nabla r psi a GUA. Now GUA, if you remember, this was something of order 1 at large r. And psi a goes like 1 over r. So hit by an r derivative, this goes 1 over r squared. And so it's more subleading than these other two terms. So I'm going to drop it at that order that I'm working with. And now, in order to go to the last step, we need some Christoffels. So the ones that show up in these u and r derivatives are gamma u, u mu, which is 0, and gamma r, r mu equals 0, so very easy. So this then just boils down to the partial derivative, nabla u psi u, minus the r psi r. We made an ansatz here that psi r is of order 1. And so this will be, well, the first term would be 0, and the next term, which will go like 1 over r, would again be suppressed. So this would also be of order r to the minus 2. So the only thing that remains at leading order is du psi u, and this tells us that psi u is not just a function of u and xa, but it's just a function of the angles. All right? Is this clear? Okay. Then there's a homework exercise for you. And the homework is to do the last step in this computation that is needed in order to find the asymptotic symmetry group of asymptotically flat space, which you can by looking at the trace of the metric. So the angular part of the metric should have vanishing trace. And so this means that when you act with a Lie derivative and then you contract this to get the trace, that this should be 0. And if you work this out, there's one Christoffel that you need, which I'll give you, which is UAB. If you work this out, you should find that the R component of this vector field is determined by the U component in this way. And in order to see this, you have to use the other boxes that we have derived. So this is homework. And then at the end of the day, let me summarize what we have learned from this computation. So we've learned that psi u is some function of the angles only, so let me call it f. We have learned that psi r, this is what you will learn, is given by 1/2 d squared psi u. And d squared is just the Laplacian on the sphere, right? So d mu is the covariant derivative, so d squared is just the Laplacian. And this is just a function of the angles. And then the psi a component we derived before, minus 1 over r, the a of a function of the angles. Okay? This is the way that we constrained this diffeomorphism vector field. Let me write it more compactly. So this is given by some function of the angles, partial derivative in u, plus 1/2 Laplacian on this function, d by dr, minus the a of this function over r, d by dA. And this is the final answer for our diffeomorphism vector field. So now let's look at the physics of this vector field. Yes? You mean numbers? So we just derived here, no, because we derived here that, for example here, that psi a is given exact, so we have derived it. So we made an ansatz before of how psi a should fall off. This ansatz captured translations. I didn't show you this because, okay, we're now seeing it come out in a moment. So this ansatz that I imposed in the beginning captures translations, but not Lorentz transformations. And then we wanted to see if there's something more. And that's actually the point of the BMS analysis, which is that they thought they would just get Poincaré. So if you restrict to translations, you should just get translations. But now we have this pesky function f here. How many translations do we have? We had 4 dimensions. How many translations do we have? Okay, that's but global ones. Yeah, so 4. So there's a function of the angles. It's a continuous function. It's not 4. It's infinitely many functions that I can write down. And all that we imposed was to eliminate Lorentz. So we should have gotten less. Instead, we got more than Poincaré. Well, not Poincaré, but we got more than the translation part in Poincaré. We got infinitely many more. So let's look at this. So if we have just time and space translations, so 1 and 3, now they became infinite. Yes, but then the derivation would have been much more complicated. And as I was writing down the equations, I could already see some people going like this. So good that I did not impose that we keep Lorentz in there. But you see, it's anyone that has taken GR can do this elementary exercise. There's no magic in there. You just start with the ansatz, and then you compute Lie derivatives. Yes?
I would expect the solutions to depend on at least the free data in the ansatz for the metric. You write the mass aspect, the angular momentum aspect, and the free data that are part of your metric.
So what we did here was we looked at the change of the metric as we act with this diffeomorphism vector field. And then what we said, for the gauge conditions, we got exactly 0 on the right-hand side. For the fall-offs, what I did here was to say that this should be of order 1 over r square or faster, okay? And from looking at this, we found, so we dropped all the terms that go, that do not contribute at this leading order. So the left-hand side is 1 over r squared, the right-hand side has potentially something of order 1 over r squared, maybe order 1 over r, then this would have to be exactly 0. And then more subleading terms. And by imposing that the right-hand side goes at least as order 1 over r squared, we found that this guy, we found that this guy has to be independent of, well, u and r. So there is still some freedom in there because we haven't said yet what this f is. But it does not, so it depends on the way that the metric falls off because we want to impose those fall-offs. But it doesn't depend on the specific metric. Once you have fixed what the fall-offs are in 1 over r, then you can figure out what the fall-offs of the vector field are in terms of r. But then there's still a freedom and in the u and the angle coordinates, as we had for the free data. There was still a freedom in u and the angles that we did not fix. If you pick a specific spacetime, it will fix for you what that is. But if you say, I have a class of spacetimes that fall off like 1 over r in this way, then those capture all of them that differ in their u and x dependence. Okay. All right, so where are the translations? Well, the translations are just given by looking, so we can find the basis for this function f on the sphere in terms of spherical harmonics. And the translations are then hiding in the 0 and 1 component of the spherical harmonics. So the y00 component, which is just a constant, let me write it that way. So f of y00 would just be d by the x0, so time translations. And as we saw yesterday, this is also translations in u. The YLM with L being 1 and M being 0 is just a translation in the x3 direction. And then, sorry, this should be psi. The diffeomorphism in, for the spherical harmonic with L being 1 and M being plus or minus 1, that is just given by a combination of the translations in the x1 and x2 direction. So this is where the global translations are hiding. And then everything else, all the L's bigger than 1, those are the extensions. And these are referred to as super translations. So let me do this here. So the general function f of xa would be given by a combination of these spherical harmonics with some coefficients, FLM, YLM of xa. And the ones with L bigger than 1 are the new ones. And let me point out that this super has nothing to do with supersymmetry. I guess there are not enough fun words that express that something is better or more or whatever. So that's what this is. And so congratulations, you have now derived what is the asymptotic symmetry group of Einstein gravity at the boundary. Restricting to not having Lorentz transformations, we landed on diffeomorphisms that contain the global translations, but that contain also infinitely many more translations. And maybe let me draw a picture here, which is, let me look at the null cone here, where U is the retarded time, and this denotes the sphere. Then a global translation along time, so this d by du here would just be the same on every point on the sphere. But the fact that we have now translations that depend on the angles, we can have along the boundary, we can have different translations depending on which point you're acting on. And so these super translations are angle-dependent translations. Okay? Good, so we arrive at the statement that the asymptotic symmetry group of Einstein gravity is given by what's called the BMS group, which still contains Lorentz, which we have dropped for now, but we know it's there, and super translations. Now somebody asked, why don't we keep the Lorentz group in there? Let's derive the asymptotic symmetry group, including Lorentz. I will not derive this because, yeah, I don't want to threaten you with going through a set of computations like this again. So let me just give you the answer. So there's a diffeomorphism vector field that now depends on a vector field, y, and whose form I'm going to explicitly write down. So it has some non-trivial u, r, and a components, which in the Bondi gauge that we are working in has this form. And I'm claiming that this contains the rotations and boosts, or rather if you write down the Lorentz group in your Cartesian coordinates and then you transform them to these Bondi coordinates, you will land on this expression. So Lorentz looks very complicated in these coordinates, doesn't it? Yeah.
So Lorentz in top fields is what field?
Yeah.
So then originally simply
With the translations, yeah. Yeah.
So the accent is to super translation, what is the translation?
So before we had just the Poincaré group, which was Lorentz and translations. Those were just the 4 here. Then we said, okay, let's make the answers that we have as a symmetry group translations. And then we went through the computation of acting with this vector field on an asymptotically flat metric, and we found that we don't just get translations, we get infinitely many more. And so in our original Poincaré, we have to also add this infinitely many extra translations, and so it's no longer called Poincaré, it's called BMS. So that's what I'm doing here. Then I'm telling you, well, we actually have just looked at this part here. Let's put back the Lorentz group. And Lorentz transformations are generated by other diffeomorphisms than the ones that we have just derived. They're generated by diffeomorphisms that look like this, which depend on some vector field that is also just dependent on the angles. So like this function f over there, which is just a function of the angles, this vector field is just a function of the angles on the sphere. And you can recast Lorentz transformations in these Bondi coordinates in this way. So let's look at where they are. So if you choose a vector field YA that is a global conformal killing vector, on the sphere, then you get the Lorentz group. So in order to look at this, let me choose, now instead of working with theta and phi as the angles, let me pick complex coordinates z and z bar on the sphere, which are related to theta and phi in the usual stereographic projection. And the z bar is nothing but the complex conjugate of z. So these are stereographic coordinates on the sphere. And in these coordinates, it's easy to write down what a global conformal killing vector on the sphere looks like. It's given by something that has at most a quadratic dependence in this coordinate z, such that the global conformal killing equation is satisfied. In these coordinates, that means that the derivative with respect to z bar on this vector field yz vanishes. So that's the global conformal killing equation in these coordinates. And let me maybe pause for a moment and look at why this is the form that it takes. So for a global conformal killing vector, in principle, I could start with an ansatz that has z to some power, d by dz. But if k is smaller than 0, this is singular. Where is it singular? It is singular where z equals 0. Okay? So this would be my general ansatz for a vector field yz. But if k is negative, then this would vanish, this would blow up when z equals 0. Let me call this the north pole. It would also be 0 when k is bigger than 2, but now at the south pole, which is at z equals infinity, south pole. And why is that? So I don't know if you remember from your CFT course, but if you do a conformal transformation and take z to some coordinate 1 over w, then zk dz goes to minus w to the 2 minus k dw. And so in these coordinates, you see that this would be singular when k is bigger than 2. Okay? So if I make this general ansatz that yz should be z to the k, d by dz, I find that the only values for which this is non-singular is when k is smaller than, when k is bigger than 0 but smaller than 2. And that lands me on this form here. Okay? So this is the form of a global conformal killing vector on the sphere. And the claim is that this global conformal killing vector field gives us rotations and boosts. And I leave it to you as an exercise to plug in this vector field and check that it is consistent with what you know about rotations and boosts. You could do this by starting with rotations and boosts in Cartesian coordinates and then mapping it to here. And then this is what you should find. Okay. So now we find that when we have translations that get upgraded to an arbitrary function on the sphere, and we have Lorentz transformations with this particular vector field, then we have what's called the BMS group. And this is an infinite extension of Poincaré. Yes? Yeah, so the algebra of these super translations, thank you for asking. So a super translation with a super translation at leading order at infinity vanishes. A super translation, super translation with rotation does not vanish, it does not commute. Yeah, and that's it for now.
So can you just repeat, do we include the super Lorentz transformation here?
Aha, super Lorentz transformations, what is that? It's going in the right direction. So we have talked about translations and found that there's no way we can just have translations. We have to have more, infinitely many more. Now I'm telling you, well, add this infinitely more translations and just add the Lorentz group with this vector field, and you get BMS, and that's it. What are super Lorentz transformations? Well, you might wonder, can I, similarly as I enlarge translations to super translations, can I also enlarge the Lorentz group? That's the question, indeed. And indeed, there are proposals that this is what you should actually do. And this is actually one of the cornerstones on which the celestial holography program builds. Let's look at why this is so. Okay, when we have this vector field yz be not just this particular function with at most 2 powers in z, but an arbitrary function of z. So this is arbitrary. Before I wrote everywhere f of xa and so on. Now I have switched to xa being z bar. So every time I write yz of z, it means it is a function of the angles. But since I'm not writing z bar here, for the moment, I'm just focusing on holomorphic vector fields here, which can be now any power of z, okay? So this would go beyond this global conformal killing vector field. And let me say, so this is holomorphic up to poles, right? We just saw that this becomes singular when we don't choose this form. So there ought to be some poles somewhere. And what that means is that I'm now extending the Lorentz group to something else. You want to give it a name? We extended translations to super translations. Now we extend Lorentz to, well, I guess super Lorentz would be natural, but for historic reasons, this has been coined as super rotations. And what this does is it extends this BMS group to an extended BMS group. Not kidding, this is the name that has been given, extended BMS group. And what we want to check here is that the fall-offs of the metric when we act with such a super rotation are still satisfied, at least up to these poles. Okay, so now again we do this fun exercise. So we want to ask if we can satisfy the BMS boundary conditions at least up to these poles, so up to some isolated points. That's the question, so let's check this. So here we are dealing with the angle parts of the metric, so z and z bar are the angle components. And we know that the angular part of the metric, if we now act with the Lie derivative of some diffeomorphism vector field that depends on y, let's say we look at the metric component G, Z bar, Z bar. That's one of the components. This component, so remember we have GAB, R square gamma AB, plus R CAB, plus dot, dot, dot. This thing in ZZ bar coordinates has just off-diagonal components. 2 over 1 plus z bar squared. The form doesn't matter, but this is just to say that it's vanishing when when this is zz or z bar. And that means that the leading term here is just of order r. So when we act with this vector field that depends on superrotation, then this should be of order r and no more. So this is the condition. Now we work this out. I give this as an exercise. The only components, the only terms that will remain here after you plugged in how this acts, looks like this: 2r squared gamma z bar partial z bar acting on yz. And so you see now that the right-hand side goes as r squared. The left-hand side tells us it should go as order r. So what do we have to do? We have to set the rest to 0. So that means, so this is gamma cz bar, so this is non-vanishing. So what has to be 0 is this piece here. Let me write it down again. So d by dz bar of this vector field yz has to vanish. So this is if you want the BMS fall-offs to be satisfied. Okay? So let me make now an ansatz for our superrotation vector field. So it can be a sum with coefficients Cn, z to the power n. We call this a local conformal killing vector. So an example of this is, so this is an infinite sum, 0 to infinity. So this is an infinite sum. So an example of such a vector field would be if I choose some coefficients such that this is given by 1 over z minus w, where this w comes in by choosing these coefficients. So this is one such vector field. This vector field satisfies that the partial derivative with respect to z bar vanishes everywhere except where z equals to w. Okay? So this vanishes up to a point. And if you have taken your CFD course, you will know that this is given by a Dirac delta at c equals w. So it's 0 except where z equals w. So this almost fits this condition here. If you restrict our local conformal killing vectors to global conformal killing vectors, which we do by restricting the range of k to give us this form of the vector field, so order z to the 0, 1, and 2, then we're back to Lorentz transformations. But we can extend Lorentz transformations to an infinite dimensional symmetry by allowing for local conformal killing vectors. And these satisfy this condition that the fall-offs are preserved up to isolated points. So this defines the extended BMS group, which is now super translations together with these local conformal killing vectors. I've written out here just the meromorphic ones, so holomorphic up to these poles, but I could also write down vector fields yz bar, where now I replace everything by the BART, by the complex conjugates. So we will get 2 copies of these special superrotations here. And maybe someone remembers some place where in your master level courses where vector fields like this have shown up. To the CFD, that's very good. And what do you have in 2D CFD when you have like vector fields like this, and this has to do with symmetry? What? Virasoro? Did I hear that, or did I make, yeah. Virasoro, yeah, very good. So this kind of smells like there may be some Virasoro symmetry going on here, okay? In this case, there is no central extension, so it would be a centerless Virasoro. But indeed, we would have two copies of some Virasoro symmetry in Z and in Z bar, and then we keep super translations. So this is what Barnish and Trossard, so I would call it the Barnish-Trossard super rotations. They extended the Lorentz group to include two copies of centerless Virasoro that are given by these meromorphic vector fields, which preserve the fall-offs up to isolated points. Now, somebody asked me before about, I made a comment about coordinate-dependent or coordinate-independent ways of talking about asymptotic flatness. So here you might say, well, if I violate these boundary conditions even at points, then isn't that bad? Doesn't that destroy asymptotic flatness? Well, if you do a coordinate-independent way of defining it, then you will actually see that the story is less severe. And let me hold that thought for a moment and extend this a bit further to bring home the message. So here we have vector fields y of z and y of z bar. What about if we put them together, if we make something that is even non-meromorphic? So what about vector fields yz, which are dependent on both z and z bar? This defines another extension of the BMS group, which is called generalized BMS. Very original name giving. And now because, so these are dependent on like a circle, this is now dependent on the sphere. So these are diffeomorphisms on the sphere, on the two-sphere. And again, we have super translations. And this is the extension of BMS that was proposed by Cambilia and Lada. So I should say that this was in the 60s, I think 62. This was around 2011, and this was, I think, around 2015. So you see there's quite some time that went on between extending the translations to extending Lorentz transformations. And it is motivated by what we have learned about two-dimensional conformal field theory in the meantime. Yes? Yeah, the generalized BMS group is defined by not just picking a holomorphic and an anti-holomorphic vector field, like separately, but looking at vector fields that depend both on Z and Z bar. And something that relativists like to do is they like to focus on smooth vector fields here. So you can focus on smooth vector fields on the sphere, as opposed to these ones that are singular at a point. And so now there are two proposals for how to extend BMS to include something super about Lorentz. And a priori, there are two distinct extensions. And it is an open question. There's open questions related to both these symmetry groups, these extensions. And I will get back to important open questions in the context of infrared divergences probably tomorrow, by the end of the day or tomorrow. Yes? You can think about a coordinate-independent way to talk about asymptotic flatness. The keyword there is something called peeling. This is a way to define the notion of asymptotic flatness. The comment that I made here, so these ones sort of violate these fall-offs that the angular part should not, so that the condition was that if I act with a superrotation, it shouldn't touch the sphere metric. It should only act on these 1/r corrections because the sphere was part of the Minkowski piece. So we only want to act on these. And we have learned that if we do these Virasoro superrotations, then it's almost satisfied. They almost don't change it except at a point. So when this is not satisfied, you see that these components, turn on a term that is higher order than the subleading piece, and so it changes the leading sphere metric. So there will be a modification of the sphere metric. So you might say this violates the fall-offs, and if you choose now a vector field that is dependent on both z and z bar, then it modifies the sphere metric not just at a point, but everywhere on the sphere. I have not shown this, but we'll write down the action of BMS in a moment. You will see that this gamma AB gets modified. So here it looks like as if the boundary conditions are violated, and maybe you might say this is bad. But in a coordinate-independent way, you can see that you can define a notion of asymptotic flatness that is still preserved when you act with these smooth diffeomorphisms. So one thing that has to be true in asymptotically flat spacetimes is that the Weyl tensor vanishes, and it continues to vanish if you act with these. So in a sense, you're changing your frame, you're changing the sphere metric, but all the rest of the behavior of these 1/r corrections is fine. But I don't have time to do that. So this is to tell you that we have extended translations to BMS, then we have extended Lorentz to two a priori different notions of superrotations. And well, you might ask how well motivated is this? And we're gonna give a very good motivation in the second lecture today. But let me just pause here for a moment and come back to this point about 2D CFD. So these Virasoro superrotations smell like some symmetry in a 2D CFD, Virasoro symmetry. That means there should be some sort of stress tensor in a 2D CFD. I hinted to you that a potentially holographic description of asymptotic flat space could either have some theory living on a space-time that is the same as the one at the boundary here, but weird things happen on this null boundary. We had this Carolian structure with the degenerate metric that means that some things either vanish or blow up as you go there. So it's a kind of weird space. Maybe I should mention at this point, if you think about putting a quantum field theory on such spaces with Carolian structure, you could obtain them by ordinary quantum field theories in the limit where you take the speed of light to 0. That's a bit weird. So it means that the light cone closes up. And as you try to run, you will never get anywhere because the speed of light goes to 0. So this seems like a weird theory on such null boundaries. There's a way to avoid thinking about this, at least at first, which is by looking at the sphere that exists at every point on this boundary. And we will find evidence in the second lecture that actually physics in the bulk may be imprintable just on this two-dimensional sphere on the boundary. And now that we're talking about this two-dimensional sphere, the celestial sphere, coming back to this point about 2D CFD, well, couldn't there live a two-dimensional conformal field theory on this two-dimensional sphere? Wouldn't that be excellent? That would be what we would really like to have for a holographic dual to quantum gravity in asymptotic flat space. And if it's two-dimensional, even better, because we know two-dimensional field theory very well. There's textbooks that you can use to kill someone that have so extended knowledge about 2D CFD. It would be really great if we could just use all this knowledge and apply it to quantum gravity in flat space. That would be marvelous. Okay, we will see some hints that some form of this may have actual legs, but we will also see that there's some more exotic aspects in this proposed holographic duality. Okay, but this is kind of encouraging, and so let's run with it. Yeah.
So on this comment, last time you mentioned that on the boundary is S2 times R.
Yeah, so the boundary is all of this, right? So the codimension 1 boundary of some d-dimensional or 4-dimensional asymptotic flat space is this null direction here. and the sphere.
So you're saying this extended to generalize here has to these are atoms has to.
Yeah, because these vector fields are just functions on the sphere and not functions of U, but they act on the full boundary because of the, there's U dependence in there, explicit U dependence in this vector field. But what I'm saying here is that, well, if you just look at the vector field, this vector field smells like some Virasoro symmetry. This is only dependent on sphere coordinates, so this should be a symmetry on the sphere. So couldn't it be that there is some two-dimensional conformal field theory living just on this on a sphere, whose holographic dual description is quantum gravity in flat space that has 2 dimensions more? So usually in ADS-CFT you have codimension 1 duality, right? You lose one spatial direction as you go to the boundary. Here we have a null boundary, so it's a bit. Good. So we'll get there. We get there. Yeah. We will talk about that. Okay. So how are we doing? Can we do a half marathon and continue, or do you want a break? A break? 5 minutes. Do something, tell us something interesting. So let's look at how they act. So let me write this down. So you have to look at the Lie derivative again with respect to this vector field that, okay, I guess I erased somewhere. And you have to act with that on your metric. The metric, if you remember, contains these coefficients CAB, well, M, NA, and CAB. Let's remember what those are. So M was the bonding mass aspect. This was the 1/r component in GUU. And A was the angular momentum aspect. That was the 1/r piece in the UA component. And then the CAB was the leading correction to the angular component of the metric after the term that is the celestial sphere metric. And all of these depend on U and the angles. And Einstein's equations constrain the bonding mass aspect and the angular momentum aspect, depending on what your matter input is. Now, let's look at how these guys change upon acting on your metric with a supertranslation. So again, you take the Lie derivative, you act on the full metric, and then you look at the components where these guys show up, and you see how these coefficients change. Because let me say this again more, to be very clear. If you the metric falls off in a certain way, and these are coefficients of these fall-offs. These are arbitrary coefficients in terms of U and the angles, except for the constraint from the Einstein equations. So if you act with a diffeomorphism vector field, if it is to be an asymptotic symmetry, it should preserve the fall-off, which means the form of 1/r, but it can change what these functions are in terms of U and the angles. So if I act with a supertranslation on the metric, it will take these coefficients and potentially turn them into some other coefficients, which still depend on U and the angles, but the functional form in terms of 1/r is unchanged. So let me denote this. So you do the Lie derivative, your homework, and then what you find is the following. So let me write this out in some detail so you have something concrete to stare at. So this is the variation for a supertranslation with some function f. And again, this is nothing but acting with the Lie derivative on the metric, and then pulling out the piece that changes CAB. So this angular piece. So this looks something like this. There is this function of the angles f, du CAB minus 2 dA dBf. I realize I don't have space enough here. Plus gamma AB d square f, the covariant derivative squared, so Laplacian. Yesterday we talked about the bonding news, which was the U derivative of CAB. And the square of that, so NAB, was the energy flux, the gravitational flux. So by taking a U derivative of this variation, F is independent of the angles. So these two pieces go away. And so we can say that the news under a supertranslation changes in this form. Okay? Let's also look at the bonding mass aspect and the angular momentum aspect. So I'm just writing down the full form, and then we're going to do an explicit example to see what that means. So you see in this whole business There are lots of complicated expressions, but that's just how the trade works. And so on the angular momentum aspect, there's another not so nice looking formula here. Oops. Okay, and that's just what it is. So this is the way that BMS supertranslations act on these coefficients CAB, M, and NA. Let's do an example. Let's say we start with Minkowski space. No one over R, just flat space. Most boring thing you can think of. Well, what are these coefficients in Minkowski space? 0. Those are the 1 over R fall-offs. There are no 1 over fall-offs, so they're 0. If the shear is 0, then so is the news, because it's just a U derivative. So everything's 0. Okay? So now we super translate it. You can tell me now how these coefficients change. So what happens to the Bondi mass aspect? 0, that's right. So it was 0 and it's still 0. What about the news? 0. So our new M and NAB are 0. So I'm still using the same letters, but those are the new ones after the super translation. And that's good. Why is that good? Well, remember, what is NAB squared? The energy flux. What would happen if I turn on an NAB with the super translation? It would mean that the diffeomorphism can generate gravitational waves. That doesn't sound like, that sounds like garbage. So indeed, it doesn't do that, and that's what we expect. Diffeos cannot create gravitational waves. Okay? Yeah?
So arguably, you could say, since that is arbitrary, I could put, for example, 1 over M or 1 over NAB in the form of a function, so that they cancel in the variations, so you don't get to it, right?
I don't understand what you mean.
For example, they cancel proportional to 1 over M, right? Or something like that. And in those
F here is an arbitrary function.
yeah, right. And you could imagine.
But it's not a function of U, but M depends on U. M is a function of U that has the time evolution, which is given by the 0,0 component of Einstein's equation. So F does not depend on U, and so once you plug in this as the initial values, this is just what you get. What about the shear? Is that 0? Can't hear you. No, okay. Okay, so what is it? It's this expression, 2 dA dB of the function f plus gamma AB d squared f, and that's not 0. So that means that our new CAB is not 0. But we just said that NAB is 0. Is this consistent? Is it consistent that this is 0 and this is not? I can't hear so well. Doesn't depend on U, which means that what we call this diffeomorphism is that it is a pure diffeomorphism. So this is consistent. The news vanishes, but CAB does not. Except there is a way that CAB vanishes. Can you tell me what that is? Exactly. So there are some special ones where CAB is 0. So what if F is a constant? Okay, obviously then this vanishes, right? And what was the physics of F being a constant? We discussed this before. Like a special choice of your super translation where F is a constant. It's a time translation in U. So it's the simplest of the 4 translations. Then we had some other special Fs, some YLMs where L is 1. So those were 3. If you work this out, you find that this also vanishes for those 3. So when F is a global translation, then CAB vanishes, and this is as it should be. Okay? Nothing should happen if we do a global translation, yet something happens when we do a super translation. So let's look into this a little bit in more detail. So this CAB, we can simplify the expression for CAB if we have vanishing curvature, which is the case in this case. So if curvature is 0, then we can write CAB as in terms of a scalar function in this form. So there's some scalar function C. This is just what you find when you turn off the curvature. And in this form, this function C, because it makes the shear component non-vanishing, when you start with Minkowski space, so you pick Minkowski space, you pick it as your vacuum, you do a super translation, you find that there's a component that is turned on. And so what this tells you is that C is kind of like a Goldstone boson. Of a spontaneously broken super translation symmetry. And we call it a Goldstone boson because the transformation of this function C looks like the one for a Goldstone boson. So if you take what I've written here and you replace CAB by this function C, then you can easily read off, because this has the same form, that the variation on this function C is just the super translation parameter F. And why are we talking about super translation symmetry being spontaneously broken? Well, we derived that this is an asymptotic symmetry, but we just saw that if you act on it, if you act with it on Minkowski space, which we may define as the vacuum, then they're broken because you turn on a CAB. So it doesn't leave Minkowski space invariant.
If you take the trace of this delta FCA, do you have something
to say about F? So CAB is traceless. This is 0. And does it say something non-trivial about F? It tells you that d square F is 0. So it gives a special form for F. Okay, and so the point here by introducing this C is that different values of it label different gravitational vacua. So we started with Minkowski space, we did a super translation, we turn on something, and so that something tells you that you're no longer in exactly Minkowski space, you're in this super translated space. And if you repeat this exercise for some more general spacetimes, well, you will find something else here. And in general, you may turn on all of these coefficients. All right? Yeah, this is some a bit cavalier here. But you think of, Minkowski space as empty, and we're gonna later talk about the S matrix where we then create particles. So you start with Minkowski space as the empty space. I don't know how to ask a question. I will make more comments about this later on. This is a subtle point. I'm being a bit cavalier here. Okay, so now I told you that this parameter C labels different vacua. And then there is a symmetry that is spontaneously broken because it even takes Minkowski space to some supertranslated space. Now, whenever we have a symmetry, we have a conserved quantity. And we discussed in the very beginning for isometry that we can construct conserved currents and conserved charges from there. So now let's discuss the conserved charges of these asymptotic symmetries. So the buzzword here, the formalism that lets you compute gravitational charges is called the covariant phase space formalism. I'm going to just sketch how this works. So you start with the Lagrangian. Let's say we start with the Einstein-Hilbert Lagrangian. Maybe we add some matter fields, for example, some scalar matter. Then that's our Lagrangian. What you do is you want to put the Lagrangian, you might want to massage it, and put it into a form such that you get the equations of motion of all your fields. So phi here would denote, so phi will contain for us the metric, g mu nu. Then maybe some scalar fields phi that you want to include. You could include gauge fields, whatever you like. You want to construct charges in this, using this covariant phase space formalism for a set of fields with some particular Lagrangian. You can take the variation of the Lagrangian in field space and massage it in such a form that you have something that looks like the equations of motion times the variation of the fields, plus something that is a boundary term, which depends both on the variations of the fields and the fields. So on shell, these Euler-Lagrange equations, Lagrange equations of motions will be 0. And you will have this boundary term here. And this boundary term has a name. It's called the pre-symplectic potential. And it is defined up to shifts, where you take it to itself plus a boundary term. Yeah. Now, starting with this pre-symplectic potential, which depends on one variation of the field and the field itself, we can act with a second variation and construct an object that now depends on two variations, delta and delta prime, and on the fields. And it's given by acting on this pre-symplectic potential, which is itself a function on the variations, and then anti-symmetrize it. And this guy is called the pre-symplectic structure. It is a two-form in field space because it has these two variations. And it is a space-time d-1 form. So a 3-form in 4 dimensions. Okay, we introduced these things, pre-symplectic potential, pre-symplectic structure. If you integrate this pre-symplectic structure, you get something that's called a symplectic structure. So we integrate this on some Cauchy slice. So this is a Cauchy slice. So this still depends on the two variations. We integrate this over this Cauchy slice sigma. There's some volume elements and some normal. And then I'm writing this pre-symplectic structure with its component omega mu. So that's what that is. Now what you do is you have your fields, and we have discussed the fall-offs of the metric if you want it to be, BMS asymptotically flat. So you know the metric. Now we could repeat the same with any other field that we put in there. For example, scalar fields. We look at, impose how scalar fields fall off at the boundary. You plug this into these definitions here, how the fields fall off. And then we want to pick one of these variations to be one of these asymptotic symmetries. So if you take, let's say, delta prime to be an asymptotic symmetry, let's say a supertranslation or a superrotation, then, and you put in the fall-offs of the fields in here, and you evaluate this expression as you take the Cauchy slice to the boundary. So you take the Cauchy slice to infinity. Then you might get lucky and find that this expression for an asymptotic symmetry transformation, as we push this Cauchy slice, which, this is some slice like this, we want to push it to the boundary, let's say this future boundary, as well as this past boundary. If you do that, then you might get lucky and find that this whole thing can be expressed as a total variation of something. So something that depends now on this diffeomorphism vector field psi. So we replaced one of the variation by how the diffeomorphism acts on the fields, and we've plugged in the fall-offs of the fields at large R, and we have pushed this Cauchy slice to large R. Maybe lucky and have it such that this other variation just pulls out in front. So it's a total variation. If it's a total variation, so that means this expression omega is integrable. We can pull out the total variation and be left with something sensible. And if this is finite, because if this blows up, then this is infinite, so that's not very meaningful. So if this omega is integrable and finite as you take the Cauchy slice to the boundary and as you plug in your favorite asymptotic symmetry transformation, then you get an object that we call Q plus minus for whether you push it to the future or past boundary. And this Q will be the charge. Let me make a comment about what I said being finite. So it might happen that when you plug in your field fall-offs, so the metric, maybe your scalar fields that you plug in or other fields, and you plug in your asymptotic symmetry transformation, it might happen that as you push this Cauchy slice to the boundary, that it blows up. That this expression omega diverges in R. This happens. And now what do you do? Well, you could say, well, I have to go home. It doesn't make sense. It diverges. I don't get finite charges. So these symmetries that I've used here are garbage. Well, that's actually too hasty, because there is some freedom in how this symplectic structure is defined. And it turns out that by suitably shifting this symplectic structure by some boundary term little theta, you may be able to get rid of certain divergences in R here. So this was a side comment. So if you find that this symplectic structure that you compute in a well-defined manner, you just need to start with a Lagrangian and choose the fields that you want to discuss. You plug this in, you choose here that one of the variations is your asymptotic symmetry transformation. You plug in the fall-offs of the fields, you push this to the boundary. If you find that this omega is integrable and finite, you can define a charge.
So you're saying you can always define a charge?
No. No, I'm not saying you can always define a charge. The key word being it has to be integrable and it has to be finite in a suitable sense. Yeah. So if it's infinite, so it may be that when you evaluate this expression at the boundary, you find that it's like R times an integral. Let's say we push it to we look at the piece at null infinity, so you have an integral over du, an integral over the sphere coordinates, and it goes with R. So that's bad. But it turns out that there is a boundary term that itself diverges in R that you can add in a covariant way, such that if you shift your symplectic structure up there and you pull this through the equations, that this actually cancels this divergent piece. This is a delicate thing, but it is what you might call a phase-space renormalization procedure. So you just realized that the theta that you started with was the bare theta. It was not a good theta in some sense. You add to it something, and that swallows the divergence. All right, so we're gonna get back to a little bit more detail of how you actually get to the charges associated to the BMS group and extensions. But for the time being, let me just tell you what they are. So if we look at BMS supertranslations, once you have computed this omega, you find that the charges actually take a very simple form. So let me draw again the Penrose diagram here and remind you that this is scry plus, this is scry minus. And then I will introduce something that I will call scry minus plus and scry plus minus. Scry plus minus is just denoting the past of scry plus, and scry minus plus is denoting the future of scry minus. So it turns out that once you have computed these omega, pulled out the variation, and then evaluated at the boundary, it turns out that the BMS charge can be written just as an integral in the past of the future or in the future of the past. So on a celestial sphere, at these values of u and v. So for supertranslations, I label it by this function f. At the future boundary, the charge boils down to an integral of the sphere over the sphere at scry plus minus. So there's still a sphere, even though I fixed. So this is u. So this point will be at u equals minus infinity. It's the infinite past. And this is v. So this point here, scry minus plus, will be the v to infinity of scry minus. So there's still a sphere. So that's this d square x here. There's an induced metric on the sphere. And then we already kind of talked about this yesterday in the simplest form, which is that we have the Bondi mass aspect come into this. And we had this expression yesterday. We talked about the Bondi mass as being the integral over the sphere of this angular density. Now we know that we don't just have translations, we have supertranslations, so we should have this function f come in here. Because we picked here this delta prime to be the symmetry associated to supertranslations, and that comes with an arbitrary function. So it turns out all you have to do is you have to put in this arbitrary function here. And then there will also be some factors of g because the coupling comes in as well. And then similarly at the past boundary, you have the analogous expression, but now integrated over the celestial sphere at scry minus plus, d square x, square root gamma, f of x, m of v x. Okay? And this is kind of the simplest possible way that this charge could arise. Good, so now we have a charge defined at the past boundary. We have a charge defined at the future boundary. When we talk about symmetries, we would like to have something be conserved. So if we had a symmetry between the past and the future boundary, then surely we should find that the charge in the future should be equal to the charge in the past, right? So this is kind of what we would like to see. We would like to have a conservation law associated to this BMS symmetry. How can this be? So if we look at these expressions, those are integrals over the sphere. We would need to have these functions m and also these vector fields, which are evaluated at scry plus minus and scry minus plus respectively. If they were equal in the limit where you go close to I0, then obviously these two charges would be the same, okay? So this is true if M and F are related across this boundary, and they have to be related in a suitable way. So I take u to minus infinity here, I take v to plus infinity, and then I still have the angles here. And the way the angles have to be related is something that came up yesterday. The way they should be related is antipodally. So yesterday I talked about how we want generators along the null boundary, that we want them to be smooth. And if you remember, I drew this, this picture with the cylinder where we had, I0, and then we had the future boundary, the past boundary, future and the past, and they come together, so that was I plus, there was I minus, and I said if you want the generators along the null boundary to be smooth, this is a piece of scri plus in this diagram, sorry, scri minus, so this would be here. And then as I go through I0 up to the future, I would come out here. So if I want these generators to be smooth, I should antipodally relate them as we go from the past boundary to the future boundary. So my angle coordinates here should be antipodally related to the angle coordinates there. And so this is this antipolar thing that comes in here. And this is something that we need if we want to say how stuff in the past and stuff in the future is related. And we will see that, that this is a Lorentz and CPT invariant way of relating past and future quantities. Yes? Mm-hmm.
Is it I0 also inside the Quotient take into consideration what happens with I0? So I mean, the charges here is independent of what happens with I0.
Yeah, so there's several things that one can say. So you might want to say, well, okay, I'm not comfortable with null infinity altogether. I like Hamiltonian evolution and so on. I want something well-defined. Then you're someone who should work at I0. And you can do that. You can look at charges at I0. You can look at how BMS acts at I0 and so on. You might think it's easier, but actually it turns out to be more complicated. And if you're interested in how things work here, you should look into Mark Heno's papers. There's a couple of papers, and so for example, you recover the BMS group at I0, and you can look at stuff there. What I have in mind here is you start with a Cauchy slice, and then let's forget about matter that goes here. Let's just look at radiation that goes to the null boundary. So what then happens is if you take your Cauchy slice, you so what will go in here, let's say we take a constant t slice. So this will be t. And then we go to Bondi coordinates. So this omega t will become omega u plus omega r. That's just what it will be in these coordinates. And then we have to also look at what happens to this piece. So this will eventually become an integral over the null direction and the sphere with some powers of r squared from the measure. And then you can evaluate this. And as you do so, you will pick up the whole future boundary, including scri plus minus, which is the infinite past limit that goes towards I0. Of course, yesterday we blew up I0, so it's actually not a point. If you go to other coordinates, you see that there's actually some sort of cylinder that has, a past, so I guess we use coordinates rho tilde for this de Sitter part, which is outside the light cone, which has a rho tilde to minus infinity, a rho tilde to future infinity, or maybe it's tau, one of these coordinates. And then you can show that the future of this cylinder matches onto the past boundary of scri plus, and the infinite past of this I0 cylinder matches onto the future of scri plus minus. Yeah.
Can you just explain the antipodal thing between M and X?
Yeah. So I did not go into much detail. You can write down the metric in terms of retarded and advanced Bondi coordinates. And in doing so, you have also an angular piece in these coordinates. In the very beginning, I just wrote down like the metric in terms of u and v, both on the future, what's geared towards discussing the future, what's geared towards discussing the past. And in both of them, I wrote x. But if you start with Cartesian coordinates and you translate them to Bondi coordinates, retarded ones and advanced ones, you may, there's a freedom in how to, if you can choose them with the same x, and then they will already be antipodally related, the x's that you choose on the past boundary and the future boundary. Or you choose them to be different x's, and then there is a non-trivial relation that is like z goes to -1 over z bar. Maybe this doesn't make sense. We can talk about this in more detail, but it would take me now too long to sort of rederive this. But the point is, you write down and you can do this as a homework exercise. Write down the metric in Cartesian coordinates, then write them down in retarded coordinates and in advanced coordinates, and then you will see that if you pick the c coordinates to be sort of the same value, then they will already be antipodally related in the sense that if you follow a generator on scry, and you want it to be smooth, then what you call a z here, and you want to still call it z here, that z on the future boundary is actually antipodal related to the z on the past boundary. I don't know if this makes sense, but I can point you to the place in, let's say, Strominger's lecture notes, for example, where this is discussed, but I don't want to dwell on it too much here. The point is that there's a way to identify these functions and also this Bondi mass aspect between the past and the future in such a way that these charges are equal. Okay. All right, I think probably well beyond schedule, but that's okay. So now we have discussed the symmetries. We have taken our sweet time to derive the BMS super translations. We also talked about BMS super rotations. We saw that when acting, even on Minkowski space, you turn on this label C, which labels different gravitational vacua. And we saw that there are charges which you can derive in a sort of step-by-step recipe using this covariant phase space formalism. And I jumped to the final result, that is the BMS super translation charge. I also wanted to give you the super rotation charge, so let me call it the Barnish-Trossard super rotation charges. Which are something that you might guess based on what we talked about yesterday. So again, this will be some integral over the celestial sphere at the past of the future boundary, or the future of the past boundary. There's some induced metric determinant on the sphere. And now we have a vector field dotted into the angular momentum aspect. And here I have not said whether this is holomorphic or whether this is a Virasoro or a differs 2. That's the charge that you get for either one. And then the same here, scry minus plus now. And A of V and the angles. And again, there's some factors of G here. And those are the BMS superrotation charges. And now similarly as above, if you now relate the angular momentum aspect as well as the superrotation vector fields in an antipodal way between the future and the past, then you get that this charge is conserved. All right. I was told that I'm the boss of the time today since we have in total 4 hours. So what I suggest is I do one more thing and then we'll take a sweet break before we continue with the second lecture. Okay? Yeah.
So on the right-hand side here, you're integrating also this Cauchy now.
Yeah.
Why are we suddenly just integrating over the sphere?
Good. So we are integrating here over the Cauchy slice. Then we are pushing it to the boundary. The boundary is codimension 1. So there are 3, there's like, if you push it, the piece that goes to null infinities will be an integral over u or over b, and the angles. Now you can massage this expression and actually land on something that just depends on the sphere at the path boundary. I will say more about how you get there, but for the purpose of getting to some of the punchy points, I'm just going to give you this answer now. And when we talk more about what this conservation law means at the level of scattering, I will tell you how this actually comes about, okay? So the last thing that I want to tell you before we take a nice break is what is really the physical meaning of BMS? I mean, we said there's like this gravitational vacuum, you turn on some components, and we talked about symmetries, but what does it really physically mean? Like, is it observable? If it's physical, it should be observable, right? So this is the third bullet point here, which goes under the name of memory. So we're gonna imagine, we're gonna draw a nice big Penrose diagram here. We draw two celestial spheres, or like one that is time translated. And we're gonna look at a pair of inertial detectors. So consider a pair of inertial detectors near the future boundary. So let's say near square plus. And we want to be in a situation where there is no bond in use, so no gravitational flux at early and late times. But there can be in between, okay? So in between, so for u early, smaller than some u late, we turn on gravity waves. So gravity waves pass through the null boundary. And what they will do is, since there are inertial detectors, and now a gravity waves passes, they will jiggle. So they will lead to oscillating distortions in the relative separation of the detectors. Let me call this SA. So let me show this picture. So let's say there is some detectors that are separated by some distance L on the sphere. So the circle denotes the sphere. And then at some time u early, there's some flux that is turned on, and then at some time u late, we turn it off. So let's say there is, let's look at this, the separation of these detectors. So let me draw it like that. Now we have some radiation that goes through null infinity between u early and u late. And what this does is, where the radiation will go through, it will distort the distance between the detectors. So it will do that. And so what we will find ending up at the future time u late is that they are separated by the distance that they had before plus some extra delta. Now you might be surprised by that because, well, if I have some detectors and I jiggle them and then I leave, and then the detectors go back to their rest situation, the equilibrium situation, surely you might think they go back to the same one, right? You kick them, and then they settle down again, they go back to the same one. Well, it turns out that they don't. So after the gravitational wave has passed, there is a residual separation. So there is so after the gravitational wave is gone, we have a delta in the separation. So between u early and u late, and that's not 0, so it's a permanent shift. And this is what is called the gravitational displacement memory effect. So how can you see that? Well, let's use math. So we look at the geodesic deviation. So we're gonna compute so this detectors, there's some velocity, so we compute the directional derivative with respect to some velocity v. This is given by the Riemann r mu rho sigma, v nu, v sigma, s sigma, and this is the directional derivative along v, where v is the velocity. Okay? So let's compute this. So we're gonna look at the component mu equals z bar. Then what we have is, so we look at this. So this is given by vu, the velocity has only a component in u, vu, vu, the u squared acting on s z bar, and this is, the two of them give +1. And then we have the Riemann r z bar nu rho sigma, vu, vu s z. So these have to be u's, u, and this cannot be u. It could be r, but we are looking at detectors on the same celestial sphere, so there is no sr. So the only thing that we can put here is z. Then I'm gonna work this out. So working this out gives me the inverse metric on the two spheres, so gamma z z bar upstairs, divided by r square times, and now if I pull this down with the off-diagonal component, so that z bar will become a z, I switch the order of u and z, so this gives me a minus uz, uz. And then I'm gonna work this out, so this will be the only component, I work this out. This becomes plus, so gamma z z bar over r, 2r actually, du squared zzz. So I'm working out the Riemann tensor, that will be the metric inside, the metric contains the shear, so this is the thing that will come out. And so now I plug this into this equation. Again, these will be 1. And then I'll find that the second u derivative is just given essentially by this expression. So I integrate twice, and I get the separation in the angular direction being given by the change in the shear component. So you see that when you turn on gravitational waves and you look at the separation between two inertial detectors, you will find that after the wave has passed, the change in the separation is not 0 so long as you turn on a shear. If you have a shear before and the shear after, so a shear at early time, a shear at late time, and the difference is non-vanishing, then you turn on a displacement between the detectors. And this displacement is an in principle measurable effect. And actually, LIGO, advanced LIGO, LISA, these gravitational wave experiments, they have as one of their goals to measure this memory effect. And now the last thing that I will say before the break, just very short, which is, well, we talked before about this different vacua, we talked about super translations. Now I'm saying that there is some observable effect that has to do with gravitational waves, but what has this to do with super translations? Well, you look at this piece here, so the change in the shear. So let me write this out again. So we'll find that there is a non-vanishing displacement if the change in the shear is non-zero. And we've just said before, so let's again write the shear as the derivatives of this function c. So if this is non-zero, this means that there is a delta C, which is C late minus C early. I told you before that C labels distinct vacua that are related by a supertranslation. So you see that when you have such a non-trivial C, this can give you a non-trivial displacement between detectors. Wow. So we started with something abstract. What are the symmetries of Einstein gravity? And we found that there is a potentially measurable effect. And we haven't measured it yet. And this is about the very low energy physics. So the very first lecture when I said, well, we're gonna do low energy physics, or isn't that boring, don't we already understand everything? No, and we haven't even measured everything that we can measure. And we haven't even fully understood all of the potentially measurable effects that come from looking into what are all the symmetries. This is one of them. The memory effect dates back to Braginski, Thorne in the 70s and various other people. This coexisted with BMS at the same time, but only until a little more than a decade ago was it understood that there's a connection between the two. And this sort of gives this a priori weird infinite dimensional extension of translations a very tangible physical interpretation. And
saying that this can be in principle measurable.
Yes.
Don't we need to detect it at near the
Well, I mean, if I said in the beginning, asymptotically flat spacetimes are spacetimes, if you go far away from sources. So LIGO, the experiment, is far away from the black holes that merge. So it's in approximately asymptotically flat space. So this is how you set it up. Yeah. Okay, I think now it's time for a break. Is 10 minutes enough? 15. Okay.